Good day, students. Welcome to part 3 of the integration review. In this clip, we're going to be exploring the connection between the limit of the Riemann sum and the definite integral. Okay, so let's go ahead and write down the instructions for the examples. We're going to be considering two questions um, in this clip. So these are the instructions. Um, express the following Riemann sums as definite integrals. Definite integrals. And in this example, they are partitioned into n subintervals of equal lengths. N subintervals of equal length, where delta x is equal to b minus a over n. Okay. Alright, so the first part I want you to do is we're going to express the sum as a definite integral, assuming that the interval is partitioned equally, and delta x is b minus a over n. And then I want you to evaluate the integral using geometry. Okay, so you might have already studied the techniques of integration, but we're not going to use them here. We're going to use the geometric approach to evaluate what the definite integrals are. Okay, so before I start, let's just go over the general definition of what the limit of the Riemann sum is as an integral. Okay, so I'm just going to write this on the side. This is based on the assumption that we have n equal subintervals partitioned in an interval, let's say a to b. So let's see, the interval here is a to b. So this is the limit of the Riemann sum. It's going to be the limit. You have the limit as the norm of the partition approaches 0 of the discrete sum from k equals 1 to n of f of c sub k delta x sub k. You see, this limit of the Riemann sum can be written as a definite integral. Okay, so what you do here is you just simply write it as an integral. The lower bound is the lower end of your interval, which is a, and the upper limit of integration is the right bound of your interval, which is b. Okay, and what you do next is c sub k will be replaced with x. So instead of f of c sub k, it's going to be f of x, and delta x sub k will be replaced with dx. Okay, so this is how you write a limit of a Riemann sum as a definite integral. Okay, so these two basically mean the same thing. All right, so let's keep this formula in mind when we're doing the example. So let me just box it and leave it alone over here, and then we're going to be using it for the following examples. All right, so for question 1, we have we're going to do this. Let's look at this. What if we have the limit as the norm of the partition approaches 0 of sigma, the discrete sum from k equals 1 to n of 3 over 2 c sub k, 3 over 2 c sub k plus 4 delta k. So let's put parentheses here, times delta x sub k. Okay, let's say that this limit of Riemann sum is partitioned on negative 2 to 3. Okay, or negative 2 to 3. So for this one, first thing we're going to do is we're going to try and express this as a definite integral, and then we're going to use the tools of geometry to evaluate what the definite integral is, or basically the area under the curve within the given boundaries, okay? So let's go ahead and do that, do the definite integral first. So what we're going to do is this limit right here, let's rewrite it. The limit is the norm of the Cartesian approaches 0 of the discrete sum from k equals 1 to n of 3 over 2 times c sub k plus 4 times delta x of k. This is going to be the definite integral from the lower bound is the left end of your interval, which is negative 2. The upper bound is the right end, 3. You see the c sub k here? Well, you're just going to replace it with x, okay? So we're going to have times 3 over 2 instead of c sub k x plus 4. And your delta k, x of k is going to become delta dx. Okay, so this is a definite integral. So this is, what is definite integral basically is calculating is the area under the curve, 3 over 2x plus 4 from negative 2 to 3. Okay, so since we are not using integration rules here, we're going to be using geometry. We have to draw this curve, and then we're going to use the geometric formulas to compute the area under this curve from here to here. Okay, so let's go ahead and draw the curve. So the curve we're looking at right here is y equals 3 over 2x plus 4. All right, so we know looking at this is the equation of a line. The slope is 3 over 2. So we're going to rise 3 and run 2, starting from the y-intercept of 4. All right. So let's go ahead and draw what this curve looks like, and then we'll determine the appropriate geometric formula to evaluate what the area under the curve is, okay? So there goes my y-axis. Here, let me put it in the center. And then draw the x-axis. Alright, so we're going to draw the curve starting from 4, 1, 2, 3, 4. I'm going to rise 3, 1, 2, 3, and run 2. Back down 3, back 2. So, let's do another 2. Let's draw the line, the curve that we're going to be looking for the area under. So, this line right here, that's what we're looking for the area under. Okay. Alright, so we're going to put in the limits of integration is basically going to be from negative 2 all the way to 3. Okay, so we're going to be going from negative 2, this is negative 2 right here, all the way to 1, 2, 3. Okay, from negative 2 to 3. So just to give you a visual, the area from here, let me just put down, do something there. This area right here, see this tracing to the curve all the way to here. So this entire area underneath here, that's what we're looking, that's the area that we're looking for, this entire area right here, okay? So what is that area going to be? That's what we're looking for, okay? Alright, so let's see, the shape I just showed to you, what kind of shape is that? This shape, this region that we're going to be considering is basically a trapezoid, right? It's a trapezoid. So what is the area of a trapezoid using geometry? Let's call this B1 and B2. And let's call this right here, from here to here, let's call it the height. Okay? So the area of a trapezoid is basically the half the sum of the parallel sides times the height. Okay? This side is parallel to this side, so the area of a trapezoid is basically 1/2 times B1 plus B2 times the height. Okay? So this is a function, let's call it y, which is equal to f of x is 3 over 2x plus 4. Okay, so to get b1, I'll just plug in 2 into the function, and then to get b2, I'll plug in 3 into the function, then we can figure out the area underneath the curve here. Okay? Alright, so let's go ahead and evaluate it. So this is basically going to be 1/2 times, to find b1 is f of the lower bound of integration, which is negative 2, f of negative 2, plus b2, which is f of 3, the upper limit, And then the height is the distance from here to here is 1, 2, 3, 4, 5, which is 5 times 5. Okay. All right, let's find out what these are. So, what is f of negative 2? F of negative 2, basically I'm going to plug in negative 2 into the function. Remember, f of x, y is equal to f of x is a function we are finding the definite integral of from negative 2 to 3 is 3 over 2x plus 4. Okay, so f of negative 2 is going to be 1 half. Actually, it's going to be 3 halves. Yeah, 3 halves times negative 2 plus 4. Okay, and if you work that out, you're going to have this 2 cancels out with that. Negative 3 plus 4, which equals 1. Okay, and then to find the second base of my trapezoid, I'll do f of 3, which is 3 over 2 times 3 plus 4. Okay, we multiply this, you have 9 over 2 plus 4. To put this over 1, find the LCD, multiply by 2 top and bottom. So it's going to be 9 plus 8 over 2, which is basically 17 over 2. Alright, so our area, we're going to plug in these two values into this area formula that we have here. Let me give you my workspace so we don't get confused. So my area is going to be, here the trapezoid, is going to be 1 half of 1 plus 17 over 2 times the height of 5. Okay, let's make this into a fraction. Find the LCD, multiply by 2 top and bottom. So it's going to become 1 half of 2 plus 17 is 19. 19 over 2 times 5, right out of the fraction also, over 1. So we just multiply across, and multiplying fractions, you're going to have 95 over 4. Okay? So what on earth did we just find? Well, we just found out what the definite integral is. So the definite integral from negative 2 to 3 of 3 over 2x, which is the definite integral form of the limit of the Riemann sum we had in the original question, dx is equal to 95 over 4. Alright, so there you have it. Alright, let's try another example. Question 2. For question 2, we have the following Riemann sum. The limit, same condition. As the norm of the partition approaches 0, the discrete sum from k equals 1 to n of the square root of 36 minus c sub k squared delta x. Okay. All right, we're gonna express. Oh, wait. On partition on negative 6 to 6. All right. So what we're gonna do first is we're gonna express this limit of Riemann sum as a definite integral. Then we're gonna use the tools of geometry to see if we can evaluate what the area under the curve is. Okay. So this limit, let me write it down here. Limit of the norm of the partition, as the number of the partition approaches 0, the discrete sum from k equals 1 to n of the square root of 36 minus c sub k squared delta x sub k, let me take care right here, equals is going to be the definite integral from the lower bound, which is negative 6, to the upper bound, which are the left and the endpoints of our partition, of the square root of 36, we'll replace c sub k with x, so it's going to be x squared, and delta x sub k with dx. Okay? So now we're going to evaluate this area. Alright? So what kind of curve is this? 36 minus x squared. Well, let's do a real quick review on on analytic geometry. You know, if we have a situation like this, let me put this in green, we have x squared plus y squared equals 36. Equals 36. What kind of curve is that? X squared plus y squared equals 36. This is the equation of a circle of radius 6 centered around 0, 0, right? Circle with radius 6 centered around 0, 0. So there are other ways I can express this same function. If I isolate y, I'm going to have y squared equals 36 minus x squared. And when I read both sides, I'll have y equals plus or minus the square root of 36 minus x squared. Okay? So the plus is the upper semicircle and the minus is the lower semicircle. Okay, so if you notice here, all we just have is the upper semicircle of the circle centered around 0, 0 with radius 6. Okay, r equals 6. So let's make a sketch of the situation we're dealing with here. A semicircle centered around the origin with radius 6. What does that look like? So basically we have, we're going to go 6 units in all direction. So 1, 2, 3, 4, 5, 6. 6 right there. 1, 2, 3, 4, 5, 6. And then go to, this is negative 6. And then 1, 2, 3, 4, 5, 6. And then go up 1, 2, 3, 4, 5, 6. Okay? And then we just draw a semicircle in here. Alright, so there you have the semicircle. So remember, this is the upper piece, okay? This is the upper piece. This is the square root of 36 minus x squared. Because we're in the minus, then it should be the opposite direction, reflected downwards, okay? So this is the y, and this is the x. Remember, our partition goes from negative 6 to 6. So what we're looking for is the area under this curve right here. Okay, that's what the definite integral is the area under the curve in the 2D scenario, okay? Alright, now, so how do we compute this using geometry? Well, we know the form of the area of a circle. But in this case, we're dealing with half of a circle, right? So the area of a semicircle is equal to 1/2 of the area of a circle, which is pi r squared. In this case, we can clearly see that the radius r is 6. Okay, so we're going to plug this into the formula. So we're going to have 1/2 times pi r squared. Pi times r is 6, 6 squared. Okay, so that's going to be 36 over 2 pi, and that is simply going to be 18 pi. Okay. Alright, so what on earth did we just find? Well, we just found the value of the definite integral. The definite integral from negative 6 to 6 of the square root of 36 minus x squared dx equals 18 pi. Alright, and this is the value of the definite integral that we expressed as the limit of a Riemann sum in the original question. Alright, so there you have it. So thanks so much for taking the time to watch this video. Feel free to subscribe to my channel by clicking up here so you can get updates to other clips such as this. More videos can be found on myclearsurf.com. Thanks again and have a wonderful day.